about the robots that exist right now in real life. And they are a bit different from what we have here. But still, why do we need to use Blender for? The project we have is to develop these new robots. They are still very experimental. And we need a tool, an architecture where we can test all of the, mainly all of the software, all of the algorithms that run the robots. And that's where we want to use Blender for this. You can imagine it like we want to test what's inside of the brain of the robot. That's our test subject. We want to try the robots in a realistic environment and see how they react to the environment. You can think of it in a way similar to what happened in the film The Matrix. In that film, there was humans inside of a simulation, and the simulation was so good that you wouldn't tell the difference. You could live your whole life inside and never realize it was just a fake. That's what we want to do with the simulator. We cannot get the level of realism that they had in the film, but luckily the robots are not very smart yet. As long as you give them good enough data, they will not know the difference between the real world and the simulation. I'm going to talk now about what kind of robots we work with. These are real robots, what we have in the lab. And I'm going to show you how they work and how they reason about the world around them. Let's see. I'll need to do this just to show the video. Yeah. This is a rover robot, a prototype of a robot that was meant to go to Mars to explore. So its mission is to just move around a completely unknown environment and, well, just be able to get to a different position, and then once it's there, it can do some experiments. Right now, we are concerned only about how does it get to that point. It can roll around, but how does it plan? How does it decide? Everything is done using sensors. As you can see, this robot has a couple of cameras. In the front, normally they are stereo cameras. And here you can see how it takes images, and from those images, it starts mapping out the world around it. Here, it's overlaying the video with these green areas, which are what it considers it's traversable, and red areas where it cannot go. Those are obstacles. And then it starts deciding how to move based on the information. Here you will see this is the view from the camera, and these arcs are the possible trajectories the robot can choose from. It will pick the one that's the best solution at the moment, and then every step it picks another one. Using the traversability map you see at the top. But this is really good as long as it's in a flat surface. But then when the terrain starts to slope upwards, then it can switch into another mode where it uses a 3D mesh of the terrain. It also builds this mesh using the stereo information from the cameras. And it's basically a similar algorithm. It will consider the terrain it has mapped and choose the best route at the moment. However, that's not always optimal. It may run into an obstacle, and then it doesn't know what to do. At that moment, it has to backtrack, analyze all of the data it has, and replan a strategy. This whole planning of how to accomplish my mission is what we want to test. Oof. The other kind of robots we have are service robots. The stereotypical service robot would be C-3PO, as a robot that can serve a human in any way it needs. It can take objects, walk around, talk, see things, but we are not there yet. This is what we have at the moment. It's still a bit ugly, but it's almost capable of doing the same things. It also has an arm, and it can help it to grab objects. It can move around. It has cameras, and even it has screens so that you can see what it does. This is a video of that robot working, and I'm going to pause a bit so that you can see a few of the details. We have the robot, and what you can see in the screen is what the robot, the vision of the world according to the robot. That's not Blender, it's another application, it's a 3D application where the robot places everything it knows about. So the robot knows there is a human in front of him, and so he represents him with a very generic mesh. It can also know where the robot is, where its arm is, what's the position, and it considers all of this information as it takes its decisions. It has other sensors as well. This one has a Kinect, which is used to read out the movements of the human. It can consider the, sorry, that was already gone. Well, this. We have a motion capture system that can track the head of the user. That's also taken into consideration for the robot to react to what the human is doing, because its main objective is to be safe. It has to know what the human is doing so that it can plan accordingly. If the human is not paying attention, then the robot will avoid surprising the human or even hurting him. So here, if the human turns around, the robot will stop and then continue its objective when the human is paying attention to it. Also, it takes into consideration the distance to the human. There's many sensors involved in doing this, so the robot can know all of these things. And this is already something that's working, that we can do in the lab, but it's really extremely complex. All of this, an experiment, as you saw here, is awfully complex. I've seen the people who do this research, and it's not a joke. They have 2 screens in front of them with 20 terminals. With data scrolling, they have to get every single system running. And the robot itself has 3 CPUs on board. Each one does different tasks. And it really is a nightmare to get one single experiment going. It takes a lot of time, and if there is any single problem, if any of the 20 systems that are running, it fails, then everything is ruined and you have to start all over again. That's why we want to do a simulator, a more controlled environment where we can do all these sort of experiments, where we can have more liberty to do whatever we want to do, even outside of the restrictions of a laboratory. Because in the lab, we have a very limited space. We don't want to get the robots damaged, so it's always very controlled. But at some point, we want to test the systems in a more complex environment, and that's what we plan to do with the simulator. So that's the origin of this project, the Modular Open Robots Simulator. These are a few of its characteristics. It's not a simulator of every single detail. It's a general level simulator that allows us to see the robot carrying out its mission. We're not so concerned about tiny details as the very fine physical interactions of the robot and the environment or some other things. There's many other simulators that do that. So we want to test the whole of it, and mainly to evaluate the reasoning of the robots. A very important aspect is that it's modular, which means it's composed of a library of small pieces, sensors, robots, and actuators that you can put together to create the robot you want, however you need it. And then using all of these sensors, for instance, you can capture data to see the data is how the robot perceives its environment. Most of this, well, basically all of what we've done to create this simulator is based Python scripts, which have to do the job of replicating the data that comes from the real world or that is sent from the real world to the robot. Here's an example. Of how data from sensors is used. This is the same. This is already a simulator using this ROS middleware that's very common. I don't know if any of you are into robotics, but that's very, very widely used. In this environment, we have the same robot. It's called Jido, and it's mapping the world around it. Down below, you can see the 2D map it's creating of the environment. It's 2D only. It's measured at the level of this plane, which is displayed in pink. That's a plane where a set of lasers are scanning everything around. They just identify obstacles, and that's translated into a 2D map of the environment, where you can see where there is a table. Here we have, to the right, we have already that map. It has already been created, and now the robot wants to go to where that red arrow is. That one over there is the simulator, MORSE that's in Blender. This is only the display of what the robot understands of the world. There's these orange areas. That's the obstacles near the robot and the ones it needs to avoid. So it tries to move around them. And all of this is already the decision level. Here, the robot is trying to get to another destination, but a user-controlled human is walking in the path of the robot, trying to block its movement. And the robot has to reevaluate the path it had chosen to avoid the human and move around him. Just as we have sensors, we also have actuators, which is the controllers for the arm, for example, for the gripper, which allows us to grasp objects. There's the controllers that permit the robot to move around. We can provide them with instructions like go to this point or use this speed to move forward or to turn. We recently switched to the newer version of Blender. That has been a big advantage because we have these new features like better performance. Something extremely important has been the inverse kinematics inside the game engine. We now can animate the human, which you have already seen briefly, but I will show it again, which is completely rigged. But we can also read the information that comes from that rig. We can, inside of the simulator, read the pose of the human, and that's how we simulate a Kinect or a motion capture system, because we can know the position of each one of the human's joints. It was a lot of work to switch to this new version of Blender, but it's been worth it. This is, for instance, the simulated human. This is meant to take the place of real humans inside of simulator. So this one would be controlled by a user, and it can interact with the robot. Its main abilities are that you can take an object, put it somewhere else. It's just the basic abilities you need to work with the robot. As you can see, the mesh is not really good. The animation is not great, but that's just what we need. The robot cannot know anything, cannot recognize a difference. So this model is good enough for the robot to know that there is a human, what is it doing, and how to interact with it. Still, from the beginning of this project, we chose to use Blender, but there had always been doubts about why choose Blender and why not use a completely new engine. Why not build our own simulator from the ground up? But well, that could provide us with advantages, like better performance, maybe, because we wouldn't have the whole overhead of Blender, because there's a lot of Blender that we don't use. We mostly use only the game engine. We don't do very complex modeling or texturing. But well, we still do it, and it's helpful, but it also can be an obstacle. However, there is a very large interest for Blender. Well, I've seen it here. There's many conferences where Blender is being used for visualization of scientific data. That's something really extraordinary, and that brings with it a lot of interest from other people. For instance, these are all the labs which are right now collaborating in the development of this simulator. It's an open source project, so they can download and contribute. We have met a couple of times for these hackathon events where people from these labs will come to labs where we work and just push forward and decide to on new targets of what do we want the simulator to be able to do. We push on that. We decide on certain aspects of what would be good to have, how should it behave. And so it's a very collaborative effort, and it's working very well. That has given us a lot of motivation to carry on, because we now see that the choice of Blender has been a very good one. Otherwise, we wouldn't be at this point at the moment. One of the things that has come from this collaboration is this item of the Builder API. It's a tool developed by someone from another lab, from IRD in Vietnam, which allows us to build all of these simulation scenes using a Python script. Before we did all of that simply with the Blender import tools. We would import pieces from other Blender files and gradually build our robot. But that was very hard for people who don't know how to use Blender. And, well, at least in robotics, not everyone knows how to use it. So we wanted to provide an interface that can simplify all of this. And this is the API, the Builder API. Just a quick demo of how that works. This is a script that defines a scene. It's really only Python. We define a set of functions, like this one, robot. We create a new robot object from this file, which is a Blender file. And then we translate it, rotate it, and just set the scene as we want it. Here we give a position to the robot. We add a robotic arm, place it in a position with respect to the robot, and make it a child of the robot. We also configure here the connectivity of each component to the outside world, to the real components. That's also very important because it's a very delicate aspect, the communication between a simulator and the real robots. And it was not so easy to configure. Now we have, with this script, we just choose here a communication via sockets. We can choose any other middleware used in robotics. And then finally, we defined the scene and how we want it to be. If I run this, it will dynamically go and look for the files I requested, other Blender files, and build the scene as I asked it, with the robot, with the arm, and then I can start the simulation and start doing things. I'll go to that in a moment. But just to show, if I want to change the simulation, I just change this file. To give it another environment. Rotate y equals 1.5. See. Just changing a few parameters. Oh. I can get a different scene, and the arm is now in a different position. So that's very easy for new users of the simulator. So with all of this recent development, we just, I'm not even sure when, about a month ago, we released the version number 0.4 of the simulator with all of these new features. As you can see, there is support for ROS, which is important. Switch to Blender 2.59, multi-node simulation that allows us to have multiple computers running the same simulation scene and synchronizing, so that we can have many more robots running in separate computers, but it's all connected. So if a robot changes its position in one instance of the simulator, it will change in the other as well. We've done a lot of documentation, the Blender Builder API. So it's moving along very well. And now I'm going to show you a few videos of the simulation actually working with the robot software that drives the real robots. This is a video of a robot navigating. Again, this is the visualization of the robot, what it sees, what it understands, and this is the environment where it's evolving. As you can see, it maps using stereo cameras. The environment, you can see the trunks of the trees and how it avoids them. This is another very good reason to use Blender, that because it has good enough graphics. In this case, we need them because the stereo vision has to be as realistic as possible. We really do take 2 images from the cameras on board of the robot and compare them to identify the differences. That's how we build the 3D mesh of the environment, the digital terrain map. And that's how it uses to navigate. It's kind of ugly, but that's how it works. That's how the real robot understands the world. And it doesn't need much more information than that. It just knows that the flat surfaces is where it can walk. If there is any jagged surface, it means that's irregular terrain or obstacles, and it will not try to go there. This also shows how we can do experiments in a larger scale than we could do in the lab. We can make the robot advance a lot, go very large distances. We can choose to have the restriction of battery life, for instance, or fuel, depending on what we want to test. And as you can see, the environment it built, the reasoning the robot had of the environment is fairly accurate, at least as far as it needs. This video is a bit old and it's not so pretty, but it shows human-robot interaction. At least the concept. That's the displayed on that wall is the view from the camera of the robot. You can also see that in the monitor on top of the robot. And in the simulation, it can take objects and move them around. As you can see, it's not extremely precise in the grip. We don't want to simulate that, at least not yet. We just want to consider the whole task, the higher level of grab an object from this table, place it there. And then we can use the human is user controlled. So you're basically controlling a computer game character and interacting in the same world as the robot. You can take objects and place them in another location where the robot should reason about them. It should be able to tell, well, the human took this object and he has taken it somewhere else. So my world changed and it has to replan. And finally, our most complex scenario so far. This is a more complex experiment where we are testing 2 different robots in an outdoors environment. This environment has been rebuilt from real data, so it's meant to be the exact same scenario where they are going to work. We have several modules which we are evaluating. So you can see how the modules that allow the robot to carry out its mission, to navigate, to plan, and to communicate between the land robot and the helicopter. They're both autonomous. They're both equipped with cameras. And they have to carry out a fairly simple mission. Go from one point to the other. It's the land robot which has to go from one point to the other. You saw the target destination. The robot is down there, the tiny red blob. And then we give it a mission. Go to a certain coordinate. This is, again, the view of the robot. However, in this case, we have the cooperation between the 2 robots. So when we give the mission to a robot, you can see there it plans for both of them. The gray dots show the path, the preliminary path for the land robot, and the yellow dots, the white dots, show the path for the helicopter. So the first step is that the helicopter will fly ahead and use its camera to map, to create a traversability map of where the land robot can go. It will fly and consider which are obstacles, where can the other robot navigate, and then it provides it with the map, with a traversability map. Then the rover will update its plan to consider those obstacles. And then the mission continues with the 2 robots communicating. The helicopter will now fly to a different location, considering what it already has seen, and thinking, what would I need to add to this information to help the mission? Here, it can see that below there is missing information, so it will fly towards that area. This is the view from the helicopter. This is from the rover. The helicopter adds more information, and then it transfers it back to the rover. Again, they keep this communication all the time, and they keep updating all of the mission objectives, the path. All of this uses the cameras on board of the robots. So the helicopter has one single camera pointing downward, and the rover has a stereo pair. That's why you also need the information of the terrain to be as realistic as possible. This is the actual geographical information for the. Okay. Yeah, it's just about to finish. Well, the environment is fairly realistic enough that the cameras can do their job, including, well, the trees are very stylized, but they allow us to recognize them as obstacles. The same with buildings. And so, well, the robots keep communicating until they reach their set goal. It's just going to carry on like that. So this is what we have so far. We still have a lot of work to do to improve the simulator. Mainly, we need more components, more sensors, more actuators, more models of robots, but that's coming gradually. Another interesting target we have is to do hybrid simulation. Imagine the previous scenario, but we want to have a real rover, the real robot, cooperating with a simulated helicopter. we can do that by exchanging the data. The helicopter will be able to see, the helicopter will be simulated in MORSE, and it will be able to see the simulated rover as well, although the real rover will not be able to see the helicopter, because that would be that would require augmented reality, and that would be a lot more complex. But what we have, we can already do this sort of hybrid simulation. Well, we're very happy to use Blender, but if we would be so bold as to make some comments about Blender, about what would be some improvements we would like to see to improve on how the simulator works, and they could help other projects as well. Since we have had, for instance, problems with the link append, that's why we did the Builder API. To be able to produce certain sensors, we would like to see some changes to the video texture module and some other improvements in general. Well, that's all of my talk. If you have any questions, as you can see, here's the details of the project. It's open source, and there's you can download the whole source, use it if you want, experiment with it. Well, but that's the whole of my talk. Thanks a lot. Any questions?
Yeah. Two short questions.
Yep.
One is, do you introduce random measurement errors into your model to account for measurement errors in real life?
Yes, we have our sensors have an additional module, which we call the modifiers. These modules you can add dynamically as well as any other module, and you can choose to add noise or change the data of the sensors. So if you have very precise data, you can change it in many ways. You can develop whichever piece of code, in general it would be a small script, to alter the data however you want.
My second question was, I've seen some simulations with robots which have thousands of iterations to tweak the neural network
Mm-hmm.
to make robots learn more. Do you do that as well?
No, we don't do that sort of thing. In fact, it's a completely different application. Yeah, there's not many points in common, because those are robots which evolve, I guess. That's what you mean. In this case, we have static robots. They are, as you see, they are physical robots we already have, and we want to reproduce how they behave. And we will evaluate not the robot itself, but the software running the robot. Yes? Again, can you rephrase it?
Is there a scripting layer for the behavior of the real robot inside the real robot?
No, it's not scripted.
Level C or something like that?
Yeah, no, it's not scripted. The real robots will do everything dynamically, evaluate the data from the sensors, plan, and then generate the output at the moment.
You run the actual same code in Blender and in the robot.
That's the objective. That's the whole objective is that the same software that runs in the robots, that's why I made the analogy with the matrix. No. The robots run whichever software they use. We basically run the same software, but connect it to Blender instead of connecting it to the physical robot. Okay. Well, thank you very much.
depth information
Yeah.
for the video textures. Never thought of that. Might not be easy though.
No, I think it's